Hello, everyone. Welcome to day 2. I'm Lucille Savary from CNRS and INS de Lyon, and I'll be chairing the morning sessions. Our first talk will be by Hidenori Takagi from Max Planck Stuttgart and University of Tokyo, and he'll talk about magnetothermal transport in quantum spin liquids.
So, good morning, and thank you very much for introduction. It's great, to come back to Santa Barbara, finally after Corona. So this is my first recovery to Santa Barbara. So today I'm going to, to update, our, magnetothermal transport story on quantum spin liquid. And this, particular work was done in collaboration with those people here, mostly at Max Planck. In particular, Jan Bruin, Ralph Klaus, Mohamed Pagdaban, Yosuke Matsumoto, those four key players of this project. And of course, needless to say, quantum spin liquid is an exotic state of matter. Many people are dreaming of. Of course, until 10 years ago, so-called RV-based quantum spin liquid, had been a major arena for exploration of quantum spin liquid. But now we have another class of quantum spin liquid, so-called quantum spin liquid, on top of honeycomb lattice, with 120-degree bond, with X, Y, Z conflicting Ising bond. And of course, those quantum spin liquid states are characterized by exotic fractionalized excitations. And in RVD type spin liquid, people believe S equal 1 boson, fractionalized into spin 1/2, fermions called spinons. And the type, quantum spin liquid, it was, shown rigorously, spin 1/2, fractionalized into 2 types of Majorana fermions. And of course, we want to, detect, those, experimentally. And since, those, excitation doesn't have, charge, so we cannot use conventional electric transport. And of course, thermal transport is, in some sense, quite, old technique, but it emerged as kind of a modern kind of tool to study those, quantum magnets. And in an organic, triangular, quantum spin liquid, some time ago, it was, claimed, there is, a finite T-linear, thermal conductivity at low temperature, which, indicates, presence of highly mobile, fermions at low temperature. And, that was taken as, signature of, spin-on Fermi surface. And for, type, quantum spin liquid, in a, famous ruthenium trichloride, group of Yuji Matsuda, pointed out, they kind of observed, thermal Hall effect close to half, quantization, which was, taken as, kind of signature for Majorana edge state. But of course, recently, as many of you kind of recognize, controversies, debates, some doubts, on those, kind of seminal works. And of course, recently, those, controversy of thermal transport for quantum spin liquid, in part, comes from, issue of, materials and the reproducibility. And of course, it's not an electric measurement. So technically, it's quite, difficult to detect, thermal, current. And of course, normally, naively, we assume, thermal conductivity is, kind of superposition of electric contribution and the phonon contribution or other elemental excitation, and those, terms kind of independent. And the thermal Hall effect, we have, only electric, contribution. But in reality, of course, the situation is not that simple. And of course, in most of the case, phonons are dominant for thermal conductivity down to low temperature. So how to separate, phonons? And the insulating magnet, we cannot rely on Wiedemann-Franz law, and how to do so. And of course, it's clear, those two, electron phonon, couples, phonon can be scattered by electrons, drag effect. And now, people discuss, phonon may contribute even to thermal Hall effect. So in that sense, thermal probe is quite useful, but we need kind of some caution to extract, information. So having this, in mind, this talk, I want to speak about our recent magnetothermal transport, studied on putative, quantum spin liquid. And maybe first, I would like to speak about, spin 1/2, Kagome Heisenberg anti-ferromagnet, Haber-Smithite, and discuss, whether, there is, gapless excitation or not. Okay? And second, although, I gave, this kind of talk, many times, but, I cannot avoid these topics. Let me speak about, thermal Hall effect of lutetium trichloride. And maybe I try to organize, controversies and issues. And since, at the moment, people discuss, role of phonons on thermal Hall effect, let me go to kind of model system, which, does show, almost, quantized, Hall effect, in the bulk, and see how, quantum Hall effect, should look like in the electric, system and the role of, phonons. And if, time remains, let me speak about, other, quantum spin liquid, candidates. Now, let me begin with, Kagome. So, everybody believes, spin of Heisenberg Kagome has, quantum spin liquid, state as a ground state. But, whether it is, E1 gapless or G2 gapped, still, as far as I understand, big debate among, theory colleagues. And perhaps, it might be interesting to see how the excitation look like in model system experimentally. That might, help theory colleagues. And this, compound, Harvard, Smithite, is believed to be one of the model system for spin 1/2, anti-ferromagnetic, Kagome. Their structure consists of essentially pyrochlore. Okay, pyrochlore along 111 direction is stack of Kagome and a triangular radius. And they have, a spin 1/2, kappa 2 plus, in Kagome plane. And, the triangular plane by non-magnetic zinc. But unfortunately, some of our zinc is kind of chemically replaced with, kappa. And that is kind of a source of disorder. And some time ago, Yong-san Lee, he did, neutron, beautiful neutron experiment and find, continuum excitation. And, he assigned it to kind of spinon-like, excitation. Now, question is, what is kind of low-line excitation? And several years ago, a group of Takashi Imai did, NMR measurement on this, compound. And at low temperature, they find, night shift decays exponentially and showing, presence of small gap. And this gap, collapse, by applying, magnetic field of 10 Tesla. So everybody believes, there could be small excitation gap. But somehow, 2 years ago, then a group of Mendel, reported, according to their NMR measurement, night, shift, decays almost, linearly, and therefore, it is kind of a gapless, and there should be U1 gapless, quantum spin liquid with, Dirac-like, excitation. And later, a group of Imai reported, now, their data suggests, things are mixture of those two. So the situation is quite, controversial. And of course, thermal conductivity detects, only mobile excitation, right? So away from, impurities, right? So in that sense, it might be convenient, to do, thermal conductivity measurement. And in fact, there are, number of, thermal conductivity studies, done, recently. And they all report, kappa over T go to 0 at t equals 0 limit, meaning no T-linear term, absence of T-linear term, unlike, those organic, case. And of course, this kind of excludes presence of finite density of states of mobile excitation. Right? So we don't have, mobile, Fermi surface, it's finite density of states. But if, it is like a Dirac-like excitation, of course, kappa over T should, go to 0. So in that sense, this, does not, distinguish gapped or gapless, Dirac excitation expected for quantum, spin liquid. So, with this, we worked on the thermal transport of, this compound, but used a slightly kind of different approach from your previous. So we used, magnetothermal conductivity. So like a component which reacts to magnetic field to extract, magnetic component. And we used, kind of anisotropy, okay, in plane and out plane to extract, 2D component of, thermal conductivity. That's, what we did. So, our strategy is quite, simple. And here is, our, thermal conductivity data. And in plane direction, along the Kagome plane, and along, C is perpendicular to Kagome plane. And of course, all those temperatures, mostly, phonons are dominant, and thermal conductivity quite, isotropic, between in plane and out plane in direction. We don't see, big change. Okay, but like applying magnetic field, you see big difference, between in plane and out of plane. So for in plane direction, you can see visible negative, magnet thermal conductivity of 5%, thermal conductivity decreases like by, 5%. Okay. But taking a look at, C-axis, at least at the high temperature, we don't see anything, right? So there is, quite, anisotropic, in plane only, negative, magnet, thermal conductivity, which is, roughly scaled by magnetic field, linear in magnetic field, right? And we believe, this is kind of coming from, phonons, because, this region, phonon, transport is kind of dominant, scattered by magnetic excitation, but which is kind of mobile only within the kind of plane, and scattered, phonon, only in plane kind of a phonon, and which increases with, magnetic field. So therefore, we believe we captured, 2D mobile magnetic excitation through phonons. Okay. Now, if you believe me about this, then now, what we should do is kind of trivial. So we just, check whether this, negative, magnetic, thermal conductivity survives down to T equals 0 limit or decays kind of like exponentially, like, gaps, behavior. Okay? But unfortunately, at low temperature, in this plot it's not, clear, but, somehow, magnetic thermal conductivity in plane component, turned, sign, and it becomes positive. And, C-axis direction, it was 0 at high temperature. At low temperature, you see kind of, positive magnetic thermal conductivity. So meaning, below, say like, 5K, we see almost isotropic, positive, magnetic thermal conductivity superposed. So we don't know, what's going to happen to this negative, magnetic, thermal conductivity. It's not, clear. Okay. But like taking a look at low radar, at low temperature, although, you see magnetic thermal conductivity, it's not, completely isotropic. Some negative contribution seems to be superposed. So to clarify that, we did kind of a summing analysis. Since, at high temperature, magnetic thermal conductivity is linear in age, like, magnetic susceptibility. So I divided magnetic thermal conductivity by magnetic field, like, magnetic susceptibility, M over B. And also to emphasize, low temperature part, I used, kappa over T instead of kappa. So this is entropy flow. Okay. Now at high temperature, as I said, you see in plane, so this is in plane only component, negative. And, it doesn't depend on kind of a field. It's like a magnetic susceptibility, M over T. okay, magnetothermal susceptibility. But at low temperature, you see something like a Curie-like, component, which is kind of isotropic, you can see, okay? And, if you take a look at the low temperature expansion, you see, very strong magnetic field dependence, and they behave like, Schottky anomaly in specific heat, or Curie-like, magnetic susceptibility. So we believe this, positive, component, come from localized, spin defect between Kagome layers. So it's really like Curie. And if you take a look at this, Curie-like or impurity, contribution, okay, comparing in-plane and out-of-plane, you can see for the in-plane component, you see some almost T-linear negative, component is kind of superposed on top of C. Okay, impurity, contribution. So it looks like, low temperature. It is kind of superposition of, impurity isotropic, contribution, plus, some, negative, contribution coming from, high temperature part. That's what, we do read. In fact, this, low temperature, contribution, we can assign, this, to scattering by magnetic impurity. So here is, magnetic field dependence of, magnetothermal conductivity. Okay, field dependence, like that. So this is MH curve, okay? And you see, with, applying magnetic field, magnetothermal conductivity first decreases, and then goes up, and then somehow, saturate, right? And this is, textbook, behavior of, magnetothermal conductivity of phonons, scattered by magnetic impurity. And the first, decrease is kind of a so-called resonant, scattering by Zeeman split, level. And at high field, spin tend to kind of polarize, and eventually they cannot scatter from anymore. So they do kind of almost kind of saturate. So this is a quite typical behavior of phonon, scattered by local magnetic impurity. Okay? So it's really impurity contribution. But now, blue is perpendicular to the plane contribution, and the red is in-plane contribution. And you can see consistent in anisotropy, between blue and the red, and eventually you see almost H-linear contribution only for in-plane. And even at low temperature, there seems to be some H-linear kind of a component, negative, susceptibility superposed on top of this, Curie-like behavior. That's, what I do see. So somehow we do believe this 2D negative, component persists, down to T equals 0 limit. Of course, you may want to see a bit better, kind of analysis. And we assumed, magnetothermal conductivity consists of some kind of bulk susceptibility, 2D bulk susceptibility, in-plane only, component, coming from 2D magnetic excitation, and, isotropic, scattering by magnetic impurity, and some kind of scaling, factor there. And we found that, this assumption works, quite well, at least, at, low temperature. And for example, subtraction of, magnetic thermal conductivity divided P, M over P, okay, you see a parallel shift of C component and AB component. And the difference is this 2D, magnetothermal susceptibility. And you see it's quite field kind of independent, describing H-linear negative, component. So at the end of the day, we have, visible, quite, consistent negative, thermal conductivity, at, low temperature, even below 1K. And, and at the high temperature, okay, so you see 2D component like this, and it seems to be, kind of connected to low temperature contribution smoothly. This region, somehow there's a kind of cancellation of two components, and it's hard to kind of analyze things. But, those two seems to be, kind of well connected. And taking a look at the NML data, from in my group, they say, yeah, so it decays exponentially, and even at 6 Tesla, there is a kind of gap-like behavior, and below 2K, almost no magnetic excitation. But in our data, we see those, magnetic 2D, component, down to, way below 1K, below 6 Tesla, right? So that means, we have, low energy magnetic excitation, down to equal 0, okay? And which actually decreases with decreasing temperature to 0, right? And so if, you ask me, whether, our data look like, gapless, U1 or gap G2, I would prefer to say it look like, U1 gapless, Dirac-like excitation quantum spin liquid. Okay. So that's, our conclusion from that. Now, let me move to then trichloride. And then this, compound, now, it is like a stark, compound. They have, honeycomb lattice of spin orbital, coupled J1 moment. And because of orbital component, coupling is, quite, isotropic, bond-dependent, Ising, plus, some additional, components. So this, compound is believed to, mimic, that Kitaic model. And because of the additional component, at, zero field, they do show magnetic ordering below 7 Kelvin. But applying, magnetic field, you can suppress, magnetic order. And above, 8 Tesla, they remain paramagnetic, down to, T equals 0 limit. And the people discuss, this region can be viewed as, some sort of quantum spin liquid. Now, here, gets, thought, when, Yuji, Matsuda, Kyoto, reported, they see, large, thermal Hall effect, around, 8 Tesla, just above, this, magnetic, critical, boundary. And so this is, half of, quantized, thermal Hall effect. And half, comes from, we have two kinds of, Majoranas. And somehow, they kind of pointed out that, thermal Hall effect is close to half, quantized, value. And they say, it should, come from, expected Majorana edge, state. And of course, everybody got interested in. And, the group of Fan On and, we kind of try to, examine, their kind of observation. And, Princeton group, find, there is no clear, kind of a temperature plateau down to, 4K. And also, they observed, much, smaller thermal Hall effect, than Kyoto. And they say, they don't reproduce, this result. But instead, Princeton group, reported, not, thermal Hall effect, but in a thermal conductivity channel, longitudinal channel, they see a quite, complicated oscillatory structure. And, they pointed out this should be a quantum oscillation of neutral quasar particles somehow. And, the situation is, quite, chaotic. And so as a kind of material group, we jumped into kind of this business. And since, Matsuda group used, crystal, made, Bridgman technique. And the Princeton group used, crystal from kind of oak ridge, kind of grown by CVT technique. And I believe not, they have, different, crystals, but different stacking of honeycomb, layers. So to check, kind of sample dependence, we worked on two different, kind of crystals. One is, Bridgman, the same, material source, from, Kyoto. And the other is CVT, grown crystal, which was, grown at, Max Planck, Stuttgart. And first, we checked, thermal conductivity. Okay, so this is kind of, our kind of a Bridgman data. And those are kind of CVT data, including report from Princeton group. And now, take a look at this, in terms of thermal conductivity, longitudinal conductivity, Bridgman crystal, the same as, Kyoto, has, factor of 2 higher thermal conductivity. So if you define, higher the better, okay? So Bridgman somehow look like slightly better than the CVT crystal. But taking a look at, magnetic thermal conductivity, you see a kind of a complex, oscillator structure. So we completely reproduce this Princeton result, okay? And also you see a kind of a deep, exactly at the same, field, okay? But then, we check, magnetic property of, our kind of crystal. And there are kind of, sequential magnetic, phase transition. And also, spin reorientation transition, like this, here. And we found, those, kind of a deep, position exactly coincide with, those, magnetic, phase transition. Okay. So, our, conclusion is, somehow, those, deeply represent kind of, magnetic phase transition. And in this region, still, phonons are dominant. And these deeply represent phonons, scattered by soft, magnetic excitation at, phase transition. Okay. And we measured, thermal Hall effect, and we observed, large, thermal Hall effect of the order of half, quantization above, 8 Tesla. And at, lower field below 10 Tesla, yeah, although, they reach, half, quantization, but, thermal Hall effect, decreases kind of continuously, monotonically, and nothing special at, half, quantization. But going to higher field, above 10 Tesla, yeah, our resolution gets, bad, due to kind of technical reason. But somehow you see, temperature dependence gets weaker. And taking a look at temperature dependence, you see something like, kink, here. And below kink, you see, weaker temperature dependence. And by chance, if you take a look at magnitude, close to half quantized value. And from, those, we said, okay, it's not, inconsistent with, having a half, quantization within kind of our resolution. That's, what, we said. Okay. But then you may ask me, okay, so Matsuda is saying this, Ong is saying this, and you are saying this, it's kind of confusing. So maybe taking this opportunity, let me kind of a bit organize, those, kind of, data, yeah, from different group. And I think it was a kind of fair statement. Yeah, although some flavor of statement kind of different from group to group, but they are not that different. And comparing at the moment, we have 4 different family of data. Kyoto original data, and Kyoto new data, and on Princeton data, and Stuttgart data. And we find this original report from Matsuda is a bit distinct. Actually they are kind of so different from other report. But recent report Kyoto, Princeton, Stuttgart somehow agrees kind of reasonably, and they have quite broad peak around 10 Tesla commonly. Okay. And at high field, somehow it gets noisy, but you see kind of weak temperature dependent, which we claim that close to half quantized. The difference is between CVT and the Bridgman. CVT somehow kappa XX longitudinal component was half. Okay. Yeah. And kappa XY as well, CVT crystal shows, thermal Hall effect, half of, Bridgman. And as a result, those feature shows up, roughly half of, quantization value. So that's kind of a difference. Or maybe, to help you understand it, we kind of replot, all those, data into, one kind of a figure. And you see this original report, quite different from recent, data. But taking a look at like, Stuttgart data green and Princeton data red, and Kyoto, new data, orange. You don't see kind of big difference. The features are kind of quite, similar. Only the difference is kind of magnitude, factor of 2 difference between CVT and CVT and the Boltzmann, okay? And the temperature dependence as well. So I pointed out that there is some kink-like, feature and weak temperature dependence, plateau-like region kind of below. And even Princeton data, you see something like, kink, they say, up, down, but some, features, here. And below that, you see kind of weaker kind of temperature dependence, okay? And, just, plotting the same, okay? So this green is kind of statistical data, 10 Tesla. And, red is 9 Tesla Princeton. And the temperature dependence is kind of a scale, factor of 2. That, quite somewhat, similar, right? So in that sense, the difference is, both in kappa X, kappa XY, factor of 2 difference between kind of Boltzmann and CVT. Now, taking this, of course, you may say, oh, my runner is there, okay, for, kind of Boltzmann. But because of, low kappa XX, some kind of disorder, for CB crystal, disorder kills, Majorana physics. You may say so. But on the other hand, you may say, yeah, those, magnitude depends on the quality of sample very much. And the depend on sample, it's kind of continuous changes. And by chance, Boltzmann sample, such a feature happened, around, half, quantization value. So I think it was a fair statement, either, interpretation kind of possible, at this, point. Hey, yeah, and the situation is even kind of more kind of complicated. Like, from the beginning, Ahim, Leon, Lucille, they pointed out that, role of, phonon is quite important in the presence of, phonon flow and coupling with, phonon, could play, important role. And, Ahim said that, quantum, quantized Hall effect, even if, without, it should be kind of approximate. Recently, a group of Luis, Taifa, Luis is saying, oh, there is a great, similarity between kappa XX and kappa XY. So therefore, kappa XY, everything comes from phonon, flow. Okay. But of course, we cannot deny, kind of a contribution, from, phonon. And somehow, at the moment, perhaps, most fair statement going to be, somehow Boltzmann, we see something around the half, quantization, value, but, that could be accidental. So in that sense, it is not so inconsistent with, Majorana scenario, but doesn't exclude, other scenario like, topological magnon and that kind of phonon. Okay, so maybe, yeah, so my time is running up. So using 1 minute, let me flash, to kind of a slide. Okay, since at the moment, the issue of, kind of phonon kind of comes up. So we wanted to come back to, kind of model system of, quantum Hall effect. And we visited some kind of a bulk, quantum Hall system to see how, quantized Hall effect, okay, appeared in thermal Hall effect, channel. Okay, and this compound, the European manganese bismuth, some time ago, claimed to be a, bulk, quantum Hall magnet, but in reality, low XX, doesn't go to 0 at, plateau region. So it's not, canonical, quantum Hall. So close to, quantum, Hall. That kind of reality. And we checked, how those, quantum Hall like, behavior of low XY shows up in, thermal conductivity channel. Okay. And first we checked, kappa XX is longitudinal, and it was kind of dominated by kind of phonons. But you see, some kind of oscillator structure, quantum oscillation. And this is, thermal conductivity estimated using a Biedermann front. Okay. And this we used as a kind of marker of electron contribution. So this is a plot of oscillatory part. Okay, this is kind of Biedermann front. And at high temperature, you see, antiphase of kind of oscillation. Okay, so when, sigma XX is kind of bottom, you see a kind of bottom of peak of kappa XX. So that comes from phonon. Okay, phonon scattered by conduction electrons. So like a density of states low, you have peak of phonon thermal conductivity. And at low temperature, you start, seeing, in-phase kind of oscillation. That is the electric contribution. But electric contribution, you see kind of amplitude is more than factor of 2 larger. And I don't have time to discuss this in detail, but this, we are for sure, that comes from phonon drag. Okay. So because, phonon me prefers it's of the order of 10 micron now. So just, kicking, phonons, electron kicking, phonons, they just, carry heat, from, one end to the other end. That's what happened. Now this is, last, slide. Okay. Thermal Hall effect, channel. Okay. And this is, Biedermann flux. So it's a sigma XY, Hall effect. And you see, quantum fall-like, plateau here. And at, high temperature, they more or less obey, Biedermann flux. Okay. So it's hard to see kind of a quantum, almost, quantized kind of a plateau within our solution, but seems to be there. So with the lowering temperature, below 500 K, where you see quite big drag effect, you see something superposed on top of this. Okay, and it's also enhancement of Biedermann flux contribution, but something else. And we find this contribution is antiphase with sigma XX oscillation, or in proportion to 1 over sigma XX, or something like high temperature phonon contribution. So I'm pretty sure phonon contribute to thermal kind of Hall channel. That's kind of our conclusion here. Yeah. So maybe just put my conclusion. Let me stop here. Thank you for attention.
Thank you for a very stimulating talk, Silke.
So in the heavy fermion field, we frequently use phonon references. There it's pretty trivial. We just replace the F atom by an atom that is equivalent, identical, but just lacks the F. Is there any way we can do something similar here to just make a phonon reference that's very similar in terms of phonon transport, but doesn't have the spin excitations?
Yeah, of course, for specific, we do that, quite frequently.
But can you do it in thermoconductivity? I think that would help a lot to clarify the situation. When you can really measure an equivalent compound which has no magnetic excitations, but the same phonon transport. Just to pin down what part is carried by phonons, then you can better assess what part can be changed by scattering of phonons from something, right?
Yeah, of course, it's not all, but say like ruthenium trichloride, we have a number of, compounds with, same, structure. And some of them are kind of non-magnetic. Yeah, and of course, we can check specific heat, but because, low temperature thermal transport depends on quite detailed, phonons. And so in that sense, to what extent, we can address, that question. I'm not, 100% sure. But I think, I understand what you mean. Yeah.
I have two questions, on the Herbert Smith site. So at the end, how could you conclude that the gaplessness was intrinsic rather than extrinsic? I didn't quite follow that.
Yeah, because it's mobile, so I think it's highly likely intrinsic.
So if you deliberately disorder it, then you change the character of the...
That part we don't know. Yeah, of course. We believe, because, it's sort of only in plane, right? Mm-hmm. So that means, they must have kind of, at certain point, we'll define the momentum within the plane. So in that sense, we believe it's kind of a mobile kind of excitation. Mm-hmm. And we believe it's kind of intrinsic. However, as you say, we can rule out, this, somehow induced by kind of disorder. If, there could be kind of mobile kind of excitation induced by disorder, we cannot exclude.
And the other question is in the ruthenium trichloride, obviously, I mean, you could also change the thickness of the sample. How does the scaling? work?
Yeah.
With a sample
You gave me
thickness?
that question some time ago. And then now here I'm speaking to, Philip Mobile, and we try to do, slightly kind of a sophisticated, version of thermal conductivity measurement, changing kind of scale. Yeah, that's kind of an ongoing project. Yeah.
So this is the question about ruthenium chloride tree.
Yeah.
So, so if Bridgman sample and CVT samples have a different stacking sequence, then we know that the in-plane exchange interactions will be affected by this. So it is possible that the actual spin model for CVT and the Bridgman sample could be somewhat different.
Yeah, of course, if this in-plane coupling, interplane coupling, changes, your Hamiltonian.
No, even the in-plane exchange interaction can be affected by this. According to a lot of ab initio calculations, for example, that the actual magnitude of exchange interaction is different.
I see what you mean.
Yeah. But on the other hand, most of the neutron scattering experiments are done on CVT sample.
Yeah.
And that's the way that we usually put a bound on the exchange interaction scale. And things like direction of the moments and things like that. So is the Bridgman sample big enough for a scattering experiment? I mean, if that can be done, you can have a direct comparison between two different systems.
Yeah, I think, as far as I observe, they are kind of sizable. So if, somebody, makes some kind of effort to accumulate a kind of sample, similar experiment, might be possible. But I think, those Oakley people, accidentally find a quite big one. They named Nessie, and they did all experiments using Nessie. And we have to check, whether we can have, Nessie of Bridgman, crystal or not.
What about magnetization? So if you compare...
Magnetization is quite easy, yeah.
So magnetization data is basically the same between two samples or not?
At least, as far as I'm aware of, I don't see kind of any difference. And even the kind of thermal conductivity, channel, except for this, factor of 2 difference, I don't see kind of big difference. It's not, as different, as, we naively thought at the beginning.
Okay,
yeah.
Right, thank you.
Just to follow up, so the series of magnetic transitions that you saw in the other sample, not the Bridgman, you also see it in the Bridgman samples?
Yeah.
But it doesn't show up in the thermal conductivity?
No, it shows up. That's what we are saying. So you see, so this is kind of data for CVT. This is, for kind of Bridgman. This is magnetic field. And you see kind of a sequential phase transition. And you see the same, sequential phase transition in CVT crystal. And that's why, you see, kind of a dip in thermal conductivity at, exactly the same, magnetic, field.
But there are some that are missing, right? In the blue line, the blue curve, there are some dips that are not there between 4 and 6.
Yeah. So in general, Bridgman sample shows, kind of a smaller structure compared with the CVT, right? But it's kind of against the, quantum oscillation scenario. Normally, quantum oscillation, the better the sample, the bigger the oscillation. But in this case, higher thermal conductivity, smaller oscillation.
Are there any more questions for Hide? I think it's time, so let's thank Hide again and move to the next talk.